Juan Ramos, and I'm here with my partners, Dustin and David, and we're here to talk about what Dr. Tosunoglu said, the search and rescue robot. Okay, I guess it was a... Alright, so our robot is actually called Aeneas, and it's actually a Greco-Roman name of a hero who ran back into the burning city of Troy to save his father and then bring him back into safety. And we want the same ideals of that rescue to be part of our robot's rescue. We want the robot to be able to go into a situation that's dire and actually save people. Project manager, as you can see up here, is myself, with the primary programmer being David, and Dustin will be the manufacturing engineer. And our advisor, as you mentioned earlier, is Dr. Tosunoglu. So a couple of things here. As you can see up here, we want the robot to compete in the Robo Rescue League. We were talking about that earlier. Unfortunately, we won't be here, so we created a club. We'll talk about that a little bit more in the lifelong learning portion. On top of that, we want the robot to be able to be very mobile and to enter a simulated disaster environment. As you can see, the robot is very rugged, very tough, and it'll do its job very well. Some of the motivations, we actually want robots to start taking over some search and rescue positions. It's actually very dangerous when you go into these situations. We want to make sure that we minimize the loss of human life, any additional property damage, and not only that, but we want to make sure that there is a lot of research being done. There's usually a failure of translating robots from a laboratory to an actual application, and that's what we're trying to do as well. Some of the rules we covered with my partner, David.
Sure, so as part of the competition, we will have to have this robot operate in a simulated disaster environment, such as after an earthquake. It'll have to detect signs of human life. It'll have to communicate wirelessly with the operator, which you can see we have accomplished here. The sensors on it must have redundancy. It must have more than one way to detect a sign of human life, and it must be sturdy enough and mobile enough to drive on inclines. The competition that we have entered separates different challenges into different arenas. Now, the arenas have challenges that range from sensory input challenges to motion challenges. Some of the motion challenges include difficult terrains such as pitch and roll ramps. Some of the arenas do require autonomous behavior, and one of the arenas specifically requires a serial arm manipulator. The yellow arena challenges the robot to be able to identify victims, and it also has a mobility challenge in the form of a pitch and roll floor. The orange arena challenges the robot to be able to operate remotely without the operator seeing it, so that only the sensors can be used to give information about what the robot is seeing to the operator. The red arena has more advanced mobility challenges, such as piecewise flooring, which will actually fall away from the robot as you're trying to drive over it. And the blue arena specifically has the challenge for the serial arm manipulator. Here you go, Dustin.
Hi everyone. So some of the major components of our robot, first one being the chassis, which is the main body. We also have the drivetrain, which includes the undercarriage and suspension. We have the electronics, which is our wiring and power for the robot, and the control systems, which include the sensors, the computer, and our Wi-Fi. The main component here, the chassis, we chose to build this out of 80-20 T-slotted aluminum. We chose it because, one, it's strong, and also it's very lightweight. We also designed it to be very modular, that way it could be adaptable to other situations. The drivetrain, if you can see here, consists of 4 shoe assemblies, and it includes our suspension and powertrain. The major components in our drivetrain are the differential gearbox, and the suspension. You can see a picture there on the right. The differential, we went and designed it to be a limited slip differential, which would help us in turning and other things like that. Also, we chose bevel gears to translate motion from our motors out to our track system. We needed bearings inside of the case to help the differential spin freely. And also we had a spline input, which would eliminate any slippage between the motor and the differential. We also grease-filled our case to reduce friction. In the differential gearbox, we chose to 3D print it to save a little bit of cost. We chose PLA plastic because that's a simple component to use, or a simple material. And also it allowed us to have proper placement of our differential. For the drivetrain, in suspension, we chose load-bearing springs to help support the load. We added rubber inserts to help dampen some of the recoil, and it also allowed us to have minor articulation, which would help in some of the mobility challenges. Dealing with powertrain, we chose a continuous track, a drive shaft, motors, and sprockets. For the continuous track, one of the reasons we chose that was it provided excellent grip for our robot. It's also increased reliability over the choice of like wheels or something else. And it also gives us a larger footprint, which would increase stability. In the powertrain, we chose a splined drive shaft. It's also made out of aluminum, which is lightweight and strong. Splined again to eliminate any slippage between the motor and the drive shaft. For our powertrain, we went with brushed DC motors. They actually operate in an efficiency zone of 18 volts, but can be overvolted up to 24 volts and a stall current of 250 amps. That gives us a peak horsepower of about 1.5 per motor. With our sprockets, they're actually custom to our tracks. If you can see, the teeth actually fit on the inside of the track. These are also out of ABS plastic, and they're doubled for strength. I'll let Juan tell you some more about the electronics.
The four major components of the electronics are the design phase, the power harness, the signal wiring, and the battery selection. The design actually, as you can see up here, began in earnest using predominantly buck converters, fuses, and an 8-point terminal that fed out to the motor controllers. The big thing about fuses, we didn't want to make sure that all our circuits are protected, and nothing was damaged in the process. These are very expensive things. Additionally, we went with buck converters over linear voltage regulators, or JVTs, because JVTs cannot handle the amperage or the voltage we're putting through. Additionally, the linear voltage regulators are wasting about 40 watts roughly each. So if you're going to have four, that's 160 watts we're wasting from electricity coming. Additionally, our power harness, as you can see here, is about 3 feet long. It's actually what's inside of the robot itself. At the far right, you can see the motor controllers. At the far left is what hooks up to the batteries themselves. Through it, you can see the motor controllers themselves, the buck converters, and fuses before the motor controllers and as well as the buck converters. And then you can see here the signal wiring. Special care was taken with this because we have a Raspberry Pi and a Wi-Fi router. And the big thing with these two is they have very dissimilar voltages and amperage needs. So we use 2 buck converters to protect them as well, to make sure we can damage the components. Battery selection, if we actually were able to be perfectly funded, we ended up using nickel metal hydride. However, as we were self-funded, we ended up using sealed lead acid batteries. They have the same power requirements we needed, but they add to the weight. However, this is incorporated as a possibility into the design, so our design actually can easily move with the batteries. Wiring configuration is the series to get 24 volts because 2 of the motors at the top require 24. The buck converters drop the bottom ones for 18, and each is rated at 12 volts each, 7,000 milliamp hours. The control systems will be covered by David.
Sure, so there are 7 major components to the control system of this robot. The Raspberry Pi 2 Model B, which serves as the main computer of the robot. We have a Wi-Fi router, a sensor package, which includes a LiDAR, a camera, an infrared temperature sensor, and we also have hardware for motor controllers and actuation relays. The Raspberry Pi 2 Model B, like I said, is the central computer of the robot. It's a full mini computer that is the size of a credit card. It has more processing power than the Arduino microcontroller, which is the typical hobbyist level microcontroller out in the market today. It uses an open source distribution of Linux called Raspbian. It has 1 gigabyte of RAM, and it has a micro SD card slot for non-volatile memory. And you can input and take output from it via text or a GUI like your desktop computer. This is a Wi-Fi router that we use on this project. It sets up a Wi-Fi network which will allow us to actually log on to the Raspberry Pi computer from an external PC, which these 2 laptops in front of you are. And the data from the sensors can also be sent to these PCs. Now this guy spinning in front of you is a LiDAR. That is our laser-based radar. It's rotating at 2 revolutions per second, and it can take 500 distance readings per second. Now this information can be collected and used to create a map of the area that the robot is in using a system called surface level area mapping. Next we have the camera, which is live streaming video over Wi-Fi. It's the native Raspberry Pi camera module, and it's wired directly to the Raspberry Pi computer. We also have an infrared temperature sensor up here on this little green square. It uses a thermopile sensor to collect temperature data at a distance. It's connected to the Raspberry Pi, and it transmits its temperature data to an external PC via the Wi-Fi. One of the most important things that we had to deal with in this robot was mobility, and we needed to give the user control over the mobility of the robot. And the way we did that was by using this hardware. This is a Tosunoglu 18V15 motor controller. We have 4 of them on the robot. They are connected to the Raspberry Pi for signal, and they are connected to the motors to actually give the Raspberry Pi control over the motors. Raspberry Pi transmits hexadecimal numbers to these motor controllers, and the motor controllers can actually interpret these hexadecimal numbers as instructions, and that's what gives the user control over the motors. What we ended up doing is we actually wrote a program where the user doesn't have to sit there and type in all these hexadecimal numbers. The user just has to hit a key like the F key, and the motor will drive forward, or the robot will drive forward. Additionally, these front 2 shoes can actually actuate up in order to deal with some of the more treacherous terrain. And the way that we have that wired is through these relays. Now, when the relays turn on, that gives power to these 2 motors, and the front 2 shoes will then actuate up. And these relays are hooked up to the Raspberry Pi, and the program that I mentioned earlier, where the user can actually input mobility commands. The user can also input commands to have the front 2 shoes actuate up and down.
Here we have a video that's talking a little bit about what we're going to do. We did tell one of the advisory board members the velocity. It's actually 3.07 kilometers per hour. We actually wired the robot up very quickly to make sure we tested, make sure it was running. And we did a couple more tests, and the speed is actually verified. As you can see here, we have demarcation lines, 1 foot apart at the start line. We have a switch which is actually shown in the design for the electrical portion, and we have a single battery to make sure that we can test all the motors. You know, we had a design component for that to make sure that if all the batteries fed, the batteries can still run the motors. As you can see here, we're driving that up right now, and it began to pull a little bit to one side, but then it began to speed up and actually continue forward. So as you can see, our robot actually is very quick, and like I said again, 3.07 kilometers per hour, that's the speed of a person jogging. So these standards will be covered with my partner, Dustin here.
So here are just a few of the standards that we followed. One of the main ones being the Wi-Fi IEEE 802.11 A or N. Also with our grease lubricant, we went with the standard SA. To take things for awareness, obviously we want to be mindful to our environment. When recycling our batteries, we're going to follow the ISO 14040. Also, it's very ethical to help victims. That's one of the main reasons why we chose to build this robot. We wrote our maintenance manual in English, Spanish, and French, and we chose an open source design. That way it can be easily adaptable elsewhere. To put things into perspective, we do realize there are electrical differences outside of the US. However, there are battery chargers available to charge our batteries. Also, we went with easily available materials. That way, in other countries, people could adapt it to their needs. Technology is becoming smaller and more powerful. Obviously, any new technology would only play into our benefit. And also, there's increased human population growth in disaster-prone areas, so we want to increase awareness towards that. For global engagement, we actually collaborated with other teams from across the world. We did receive a few resources from the judges and the RoboCup committee. Also, we want to increase awareness of worldwide disasters and also help other first responders like the Red Cross. To engage in lifelong learning, we started a club. The club is called Panther Robotics. We engage in other activities like the outreach program, Engineering on Wheels, which is sponsored by FCA. We're also going to publish our findings in the FCRAR 2016 Florida conference. Before we close things up, we want to give special thanks to Dr. Tosunoglu, Dr. Basil, Dr. Levy, Dr. Sun, Mr. Ziccarelli, Mr. Shinde, and Mr. Khan. At this time, I'd like to open the floor to any comments or questions.
I'll start. Okay. In your problem statement, you state that you've got sustained prolonged missions without failure. What have you done on the system to ensure that this will sustain without having issues over time?
Well, I can answer the electrical portion, my partner's can answer some of the other portions. Electrically, we made sure we had batteries that had sufficient capacity for it. Additionally, we ended up choosing, as we mentioned earlier, two battery packs will be wired in series. The others will be in parallel as well to give additional power resources so that we can actually have a robot. We ended up planning some of the missions mechanically So I'll tell you a little bit more about that, but electrically, we have the power to sustain a longer mission. And as a matter of fact, repeat missions, because some of the competitions, you'll do a 30-minute competition, you'll stop, then you'll go back and you'll go do another competition. So you want to make sure that the batteries can actually survive not being recharged for a certain amount of time.
Also, if you look at most of our components, they're pretty heavy and beefy, so we actually engineered them with a high margin of safety, more so than what we thought was necessary in case other problems were to arise.
The reason I asked the question is that I'm looking at a lot of wires and a lot of snag points potential. And that would be a concern to me because you can put beautifully beefy parts on it, yet someone yanks off those wires and all of a sudden you don't have a robot. That was the concern I had.
Oh, sure. Well, right now we have it in kind of a demonstration state.
Okay. So how would you change this to compete?
Essentially, some of these components that are mounted on the outside, we'll just mount them on the inside of the robot.
Additionally, we have several sleeves that we can use. Some are insulated, some are not, and that's actually we're going to run the wires up and down. Using some of these, you can see we already actually integrated some as well through that method. Furthermore, we do have an 8-point terminal. There's a 4-point terminal at the top, and some of these can actually use as well more sleeves to make sure we have a nice clean wire profile.
Okay.
We can also solder most of the connections together, that way they won't be able to pull out.
And there are some components that we have upstairs. We didn't install them because, as David mentioned, it's a display, but they actually go here to seal the robot up on all sides. But we wanted to make sure you guys can see the robot and have a nice display. So.
Okay. Two other quick questions. One, you make in your mission statement, you say that it'll be successful at detecting life. How do you do that?
Right, so one of the competition parameters was to have some of these sensors be able to detect simulated signs of human life. And specifically in the competition, there are signs of human life are represented by dolls, actually either laying, like some of them are doing different things, some of them are laying on heating pads, which is why we included the thermopile sensor. And some are just behind light bubble, which you can see just with our camera. So the way that we detect signs of human life would be getting this information, getting this data from our sensors, and actually interpreting it.
Okay, so and then I guess the last question is avoiding obstacles. So your system is not autonomous by any definition.
Right. Right. So we're a team of 3 mechanical engineers. We didn't have a computer science background, so we thought we would get the control down first, and the autonomy would be kind of a goal for the future.
Additionally, a portion of the competition does not require, only one of the arenas has to require the full autonomous behavior of a robot. The others can actually be operated by a remote operator. So we decided to compete as a general catch-all rather than specialize in 1 or 2 arenas.
Okay, and my very last question. The drivetrain that you designed is 4 independent track systems.
Yes.
Is there adequate clearance between the tracks on each side so that they have the ability to freely move if you had a situation where you had issues? Because I think those are kind of close in the front corner, in the middle.
They're a little bit close, but we have our suspension pretty rigid. It doesn't provide too much articulation right now, so even in like full flex, they actually don't hit each other.
Okay,
Additionally, we also wanted to make sure that we took care, as David mentioned earlier, one of the arenas has simulation for rubble, and it falls up from under your robot. We wanted to make sure that it wouldn't get stuck between these portions, so we made sure we had tight tolerances on that on the robot for that purpose.
Did you keep time for the amount of time that it took you to build this and the cost? I noticed you didn't have any cost dollars up there for all the parts that you put together. And also, did you keep every time you went in and worked on this, did you sign in and log in and keep an accurate amount of time it took you to build the robot?
Well, as far as the financing portion, we do have it in the thesis. I believe it's over $3,000. Additionally, in terms of man hours, it was rather difficult because we were also managing course loads. So we would start doing homework for a class or go to class, come back, and just somehow end up working on the robot. So it became kind of one of those things where your yesterday to-do list kind of merges with your today to-do list, and you just constantly work on the robot. Additionally, sometimes you'd be on the computer, for example, doing your homework, and then you realize, oh man, I have to look up this particular component. So you open another tab and you start reading that, and then you go back to your homework. So it's a combination of, you know, constantly actively doing something and passively doing something as well. So it's very hard to gauge. However, we started building full-fledged mechanically in the summer, and the chassis was built over 2 weekends. The portion at the bottom was built over about 2-3 months, and then the harder portions were basically getting everything financially together and actually assembling it. The suspension system was one of the last things we actually did physically. So.
Well, and the reason I asked that question is because it seems to me this could be a viable piece of product in the market. Police forces, all kinds of rescue devices and that kind of thing. One of the things you have to do is you have to figure out how much you're going to sell it for. And if you don't know what it took you to do it, it's very hard to do it. One of the reasons for small business failure is not keeping track of the time it took you to do a job. So, you know, if you would do it again, it would be worthwhile to say, you might be surprised, oh, we probably had 100 hours in there. If you really logged into those minutes, you might be finding that it's 400 hours that it took you to do it. And so not having a real realization, and I think it's a very cool device, and I would think commercially it would, you could put this thing together and use it, sell it to police, you know, anybody that wants to go into something where there's human risk would be great. But I would advise you to try to do that. It's a good exercise.
Thank you.
I got a quick,
Yeah, please go ahead.
one quick comment. Following Chip's comment there, I noticed the wiring stuff as well, but if you look at the bottom, you'll have the axles and the shaft going across that could be easily caught with a rebar or something like that, and then you can't move back and forward. So you might want to cover that. I don't know how you're going to handle it.
Sure.